Okay, it is time to continue. So our next speaker is Eduard Vorobyov, who will introduce the FEOSAD code. Eduard, go ahead.
Thank you. It's a pleasure to introduce the code FEOSAD. I'm a primary developer, but it has become really teamwork since recently, and many colleagues of mine contributed pieces and bits to this code. And the code is designed to model the formation and long-term evolution of protoplanetary disks. The problem that we face when we want to model the disk formation, the protoplanetary disk evolution from formation till dispersal, basically, are the spatial scales. We have to deal with sub-EU scales to maybe 1,000 EU, and then temporal extent. It's a few million years at least. And it's too costly for full 3D simulations, well, unless we degrade the resolution and physics beyond reason. And a common solution here is to reduce dimensionality, and the Pringle viscous equation is still widely used in this context. The problem may be that it's a one-dimensional equation, assuming axisymmetric disk, but this may not be axisymmetric. So we see some structures, spiral arms, and other structures from dust emission and scattering light. And the FEOSAD is aimed to improve the 1D viscous models by adding the azimuthal dimension. So it's a full, it solves full equations of magnetohydrodynamics in this limit on the polar grid with the log spacing and the radial direction. And it's grid-based finite volume method. It solves the advection of gas, dust, and volatiles using the third order piecewise parabolic scheme, which third order accurate scheme, the golden standard nowadays for hydrodynamic codes, but it's still first order accurate in time. It also uses the Farg algorithm for accelerating simulations, and it's 1490 OpenMP parallelized. We check the thin disk approximation often, and yeah, it's fulfilled up to maybe 1,000 astronomical units. By the way, the Pringle equation has to also obey the thin disk approximation. These are equations. I'm not going to bother you with this. There are many more. Better just to go through the physics, which is included. It's a gas component, dust component, star, and volatiles at the moment. So we have cell gravity, turbulent alpha viscosity, including heating, friction with dust, photoevaporation, magnetic disk winds, ionization balance. For the dust, it's also friction with gas, growth and fragmentation, radiative cooling, it's important, yeah, turbulent diffusion, and work in progress with adding dust charges now. For the star, it's of course stellar radiation of the disk and accretion from the disk onto the star. And we can use actually couple the code with 1D stellar evolution codes if we want to see how the star evolves with time. Volatiles, at present we have 4, the main volatiles, and they're transported with gas and dust. They also can sublimate and freeze out. They set the fragmentation velocity of dust, and as of now, no chemical reaction yet. It's a notoriously difficult problem, really. So it takes about from a few days to a few months to compute the disk evolution from formation to a few million years, and it strongly depends on numerical resolution, of course, the position on the inner disk boundary. The typical run is just this resolution, and the inner grid is about 0.5 AU, but we can go as close as 0.2 AU presently to the star. What FEOSAD is good at? Well, originally it was developed to study disk fragmentation. So I'll play this animation here. And here's a snapshot. We see these fragments forming, and they migrate into star. They get destroyed by tidal torques. And because we do not introduce thin particles, we can study the internal energetics, basically, of the clumps and compare the thermal energy, rotational energy, and figure out how many of these clumps are going to be gravitational bound and actually give birth to giant planets or brown dwarfs. And usually it's a very small fraction of the total number of the clumps. Another application, nice application, we can actually study the evolution of disk masses and sizes and determine which physical processes determine these masses and sizes. So that could be self-gravity, turbulent viscosity, or disk winds. This is a figure from PP7 review paper. And as of now, we see that the trend is first the disk radius and mass are determined by cell gravity, but then it can bifurcate, and MHD winds drive the disk radius and size in disk mass below, while viscous effects, they actually spread the disk. And we try to see this trend by running different simulations models where GI plus viscous disk, but no MHD winds, but then we add MHD winds, and then just winds plus viscous disk. And we can populate, so these tracks, we can see which models actually best reproduce the observable data that is shown here with circles. We added the effects of magnetic disk winds recently, two models. One is fairly complicated based on the MHD model of BY 2013. The other is a simple alpha disk model of the bone, where just the efficiency of magnetic disk wind depends on a parameter alpha, much like a turbulent alpha viscosity. And what we can see, of course, the effect of the disk winds here is a gas disk, this model without the wind, and this is model with the wind. And the model without the wind is the disk is larger, it's viscously spread, whereas with the wind, it's more compact, and it actually makes more sense when compared to observations model. And also, we can, another simulation shows, now it's a closed, but this is a large view basically on the entire disk. Now we focus on the gas and dust. So the top panel row is gas, the bottom is dust. And we can see how the evolution of the disk, of the dusty disk, actually changes depending on the efficiency of the wind. So this fiducial model, no wind. This is a moderate wind and rather strong wind, and I will just probably scroll it further to see, just look at the dust evolution. So the dust evolution really becomes different. And with time, we see that very pronounced ringy structure forms. These are dusty rings. And whereas in the weak wind or no wind model, we don't really see that much that much detailed ringy structure. Can also couple the FEOSAD code with Radams 3D or also with Prolimo to see how the spiral structure, for instance, can be is detectable or not when viewed with ALMA, for instance. So this is a real disk, the dust distribution, a real in a simulated disk, and this is how we would see this disk if we employ ALMA, band 6, and this resolution 0.03 arcseconds at different distances. So this is a really synthetic image after CASA post-processing. So you see spirals at 140 parsec here, at distant, we still see them, but already at 700 parsecs, basically, and they are not distinguishable here at sigma contours. Dust and volatiles. This is another feature of FEOSAD. It involves dust. We have two models of dust growth, monodispersed and bidispersed growth models. They fairly good reproduce Smoluchowski, much more accurate model, I mean, much more time-consuming model. But our models also just fairly good, in a fairly good agreement with very sophisticated and time-consuming models. So here I play an animation of the dust size, maximum dust size of particles, and the lines here. The solid line is the fermentation barrier, and the dashed line is the drift barrier. with time, we see how that this grows in size, and in the inner regions, the dust size is limited by fragmentation, and the outer regions is limited by growth, by drift. And yes, if I scroll it later, then we see that's really like a nice agreement. Another interesting application, we can look for the spatial distribution of pebbles, and we define pebbles as grains with size greater than 0.5 millimeters and stalks greater 1 to 100, so 0.1. And this is how it's distributed in a disk, how it changes distribution. Now you can notice that there is a 2D element to that. So the distribution is not really 1D, it's not axisymmetric. And especially this becomes clear if we redefine this pebble distribution and require that the Stokes number be greater than 0.05, then it's really patchy, it becomes patchy. We can study the snow lines, evolution of snow lines with time, and it's not just where temperature becomes greater, some fixed value. It's really like surface densities of water, CO2 here, on gas, in gas, on ground dust, on small dust, and then here is the snow line. Its evolution with time. It's basically because we solve the full equations of transport and sublimation and freeze out. Another nice feature of FEOSAD, we have recently implemented that we added the dust size dependent opacity. So the standard is, for instance, the Semyonov opacity here is the black line, but it's for the MRN dust size distribution. So basically the maximum size about 1 micron, typical for the interstellar clouds. And as the dust size, maximum dust size increases, then the opacities change. And then they don't, that's not this translation up or down, they really change the slope. And the immediate effect that the inner disk regions become cooler and the ice lines become closer to the star if we consider dust growth. So this slide actually shows the water and CO snow lines in a gravitational stable disk. So you can see here that if we really look at the 2D simulations, then the snow lines are not circles in the disk midplane. So if the disk has structure, spiral structure, then it basically the snow lines also have this spiral structure. Another application, we often use FEOSAD for studying effects of variable accretion. This is a slide from the PP7 review paper of Fisher. And what it shows that the amplitude of the bursts and duration of the burst, basically. We know that variability is an intrinsic property of stars, and different stars show different patterns variability, but we are mostly interested in this FEORI-like outbursts, very energetic and long outbursts. You can model them using 4 different theoretical models, burst models. They're all implemented. And here, for example, they show the accretion rate and zoom in onto a burst. This is the sharp increase in the dot mass accretion rate on the star. And very interesting application, we can study how the snow line moves during the burst. On the left, I show the maximum disk size in a non-burst model. Here is very small size. This is the water snow line. And beyond the snow line, the size increases of dust, maximum size. And here it's with the burst. And as the burst comes, the snow line of water snow line moves outward, and the dust gets destroyed. Basically, we assume a multi-seed dust model. Dust grains basically break apart, and then regrow. we study these effects, and they have very interesting consequences. We also can look in the disk regions where the streaming instability can work well. FEOSAD itself cannot model the streaming instability because the guys who simulate this the streaming instability, they insist that it should have that vertical dimension. So if it's a thin disk, we cannot really do that accurately. And that's why we just apply some criteria that were derived from very sophisticated focus simulations of the streaming instability. So here shows, for instance, this plane stability, instability in terms of the dust to gas ratio and Stokes number. Now I play here, this is a dusty ring, and it shows how it is converted into planetesimals. This is the rate of planetesimal conversion into the streaming instability. You see that the massive dusty ring finally depletes. So we see only, in the end, a few rings, narrow rings are left. And then here is the mass of planetesimals. We don't have planetesimal dynamics yet. We really need n-body to couple with. If anybody is interested, it will be a very great project, very interesting project to couple with n-body to see further dynamics of planetesimals. Another recent application, we look at plane formation cosmic dawn. So what we do, we run this global simulations using ENSOR of parent stability supernova explosions in the early universe. Basically, it's a redshift of 17.6. And here's an example of this debris after this explosion, 0.7 million years. And after cooling, a core forms a dense core, which has a pretty high metallicity enrichment, 410 to the -2 of the solar metallicity, and the minimum Jeans mass about 1 solar mass. And then we take FEOSAD, and it's designed especially to model this low metallicity environments, because we have all these bells and whistles of the physics that is pertinent to that. We have decoupled gas and dust temperatures, exchange of energy between gas and dust, and hydrogen helium chemistry, non-equilibrium chemistry there. So we can model these effects, and we see that indeed we can see that formation of planetesimals in the early universe, and we form like 6 Earth masses planetesimals, and about the same amount of pebbles, but lots of dust gets actually sublimated in these very early environments. And what is most interesting, that these pebbles actually form in the habitable zone of the star, which is mass of about 0.7 solar masses. So basically, the first planetesimals can form 200 million years after the Big Bang, before really the formation of the first galaxies. And final thing that we can do, but we have never really published anything, it's just a dormant feature of FEOSAD. We can study planetary migration. So this is one Jupiter mass planet that we put into the disk. This is gas disk, this is dust disk, and it just migrates. It's self-consistent migration. So it's not some analytic prescriptions, it's just gravitational interaction between planet, disk, and star. All simulation is done in the non-inertial frame of reference of the star. And well, that any interested collaborations are welcome, because we really don't know what to do with this feature, but it's there. All right, so thank you. This is my final slide. We can use FEOSAD for instance, for long-term simulations and see the trends. Try to explain the observed trends between the disk mass, size, accretion rates versus stellar mass. It's very well, the FEOSAD can be used for that. Then we can study pebble fluxes to this partial distribution of fluxes.
Eduard, excuse me, maybe I will stop you right here, because we are quite close to the 20-minute benchmark, so that maybe we have time for one quick question, if there is any. Are there any questions for Eduard? Yes, Peter?
Maybe just a very quick one. You mentioned that opacity tables, you can make them dependent on size. And you see very clearly what I also see, what everybody sees, is that if the dust is larger, then of course the opacity gets smaller. But MRN, I think, is way smaller. So it starts with very small sizes and goes to 0.25 microns, I think. And you start actually with 0.0005 or so. So really small grains, which gives you a huge opacity. But you mentioned that is 1 micron. So can you clarify?
No, I mentioned 1 micron for MRN, the maximum size. That's what is used, for instance, in xenon opacities. In our case, we take a full spectrum from 5×10⁻³ micron to whatever maximum size. And you see here, for instance, like 1 centimeter, 1 millimeter. Yeah. So it's a full spectrum from whatever minimum we set to maximum. We have these tables, and then we look what is the maximum size in our case. And
yeah, I only want to mention that the minimum size is actually very important. So if you play with the minimum size, it will also give you a lot of change in opacity, and that's often not really taken into account. We heard that yesterday, no, on Monday, that people who do this dust evolution. So I would be really curious to see what they predict in form of the minimum dust size.
Changing the minimum dust size. Well, Peter, we can try that. We use actually that opacity tool, so you know that.
Yeah,
we can easily change it by an order of magnitude to see, right?
Remarks, often people assume very small minimum dust size, and that has actually a very important effect on your opacity.
Good, yeah, good to point. You pointed to that. We can double check that. Yeah, it's not difficult. We have scripts to do that. Thanks.
Okay, thank you. We need to continue. So thank you, Eduard, again.
You're welcome.